happy to have Miguel Campiglia tell us about BMS symmetry at time infinity.
Thank you. Can you hear well?
Yes.
Okay, thank you very much for the invitation. So I will present the ideas, some ideas of how one can extend BMS and in particular super translations to time infinity. This was some time back work we did with Alok. So just some introduction. I mean, this may be a bit outdated, but just I understand that that I should give a overview. So before, I mean, after these authors show how one can relate Weinberg's graviton theorem with BMS super translations, and in particular understand these factorization properties of amplitudes in gravity as a consequence of super translation word identities. I mean, initially this was established for massless particles, but however, this Weinberg's theorem applies both to massive or massless external states in the amplitude. So one expects then that this treatment that they gave should allow should have an extension to the case where there are massive particles. And the way we approach this problem was to first try to extend the ideas of an asymptotic phase space at null infinity to the case of an asymptotic phase space at time infinity for in order to be able to deal with massive fields. So this asymptotic BMS charges can be understood in terms of this phase space of gravity at non-infinity introduced by Jasticar and Struble, and our approach to the problem was, okay, let's try to see what should be the asymptotic phase space for massive field, and then see if we can then extend these ideas to the case where there are massive fields present in the problem. And the idea to look at time infinity was to try to parallel, or we were inspired by previous approaches to spatial infinity. Here there are some of the early references on that, where one zooms in near spatial infinity by an appropriate choice of coordinates that I will describe. So we kind of inspired by that, we were doing similar zoom in for time infinity. And I will introduce, sorry, okay, then this is what will allow us to have an extension of super translation, symmetry, and charges at time infinity. And I will introduce these ideas today in the context of linearized gravity. So then let me just start with Minkowski, flat Minkowski spacetime, and discuss two sets of coordinates that allow us to explore either infinity in the null direction or in the time-like direction. So this is just to introduce a bit notation, but it is what already has appeared in previous talks. Here this U is a retarded time, R is a standard radial coordinate, and theta A are two coordinates parameterized in the celestial sphere. So it could be theta and phi, or it could be Z and Z bar. And the Minkowski line element then in this coordinates takes this form. This Q naught AB is the round sphere metric here. And okay, and these indices, capital A, capital B are sphere indices. So to go to null infinity, we just take R to infinity, and so we keeping U and theta constant. So this, if I just draw the Minkowski space-time, time and radius, then taking R to infinity, keeping U constant, I will go in this direction. Now, to go to time infinity, we introduce this like hyperbolic coordinates. So the idea is to be able to go in time-like directions along any boost angle. So to that end, we introduce kind of the analog of spherical coordinates, but for Minkowski space. So this tau will parameterize kind of the hyperbolic radius, or which hyperbola I am sitting in, this tau. And then rho and theta a, rho will tell me where in the hyperbola where in the hyperbola I am. So it is related to the velocity of this time-like line, and then theta again is just the angular direction. So in terms of this, I will collectively call y alpha as these coordinates on the hyperboloid. So rho giving this velocity or hyperbolic angle, and sorry, this should have been and theta a the angular components, and then in this notation, the space-time metric, Minkowski space-time metric, takes the form. Takes this form. It's like having flat space in spherical coordinates, where now the role of the radius is given by this tau squared, by tau, sorry. And then h naught alpha beta here is the metric of the unit hyperboloid, which in this particular coordinates I will be working, it takes this form here. Oh, by the way, please stop me anytime. I mean, yeah, I'm trying to, I don't have so many slides actually prepared. It was just the beginning to set up notation and present ideas, but I was told this is supposed to be more of a discussion. So please interrupt me anytime. Otherwise, I will finish too fast. Okay, so okay, so to go to time infinity, what we do then, we will take this tau to infinity. We will take tau to infinity, and keeping this y alpha constant, and then null infinity will be in the we will use the first set of coordinates r to infinity, and we keep u and theta constant. Okay, so basically I mean, what we will be doing is playing between these two different limits or boundaries of space-time. So a pictorial way to describe these different limits is here. I mean, this is just, it's only a drawing to have some intuition. I mean, it's not to be taken too seriously, but this is basically like a modified version of Penrose's diagram for flat space, where we have here kind of this, we have done this zoom in or blow up of time infinity, and here also of spatial infinity. So basically, this here I'm drawing this hyperboloid that tells me the final velocities of this asymptotic time-like geodesics. So in that way, so time-like geodesics will end up here in this. Will be described by points on this hyperboloid as describing their final velocities, and null geodesics will the final point of null geodesics are at null infinity.
So sorry, Miguel.
Yes.
Hello, how are you doing? So in the this is a kind of Milne universe or something like that, no? Like this. So in H0, what you call H0, is there, I suppose, a natural way of implementing the boundary condition that you would use in the standard description of asymptotically flat spaces? So, but here you will impose something special and H plus that you can infer from some kind of symmetry from the natural boundary condition you would impose at I0, which is here blown up to H0. Or
so yeah, so I think here today I was planning to talk about just only about what happens basically at this H plus and the neighborhood of scribe plus near U equals plus infinity. So this discussion will be independent of what's happening at H0. But yeah, at the end I will comment. I mean, when we write the supermomentum, I will describe the supermomenta. So these are charges that are, I mean, these large gauge charges like BMS charges. They are defined. I mean, we define them at spatial infinity, and then we use Einstein equations to write them in terms of data at. Okay, if I'm talking about the future charge or future supermomenta, then we will write them in terms of data at scribe plus and H plus. But and I will this I will discuss at the end. Thank you. Yeah, if there is any other. Okay.
Excuse me.
Yes.
But do you have different charts to describe these different regions? You know, the idea is to use different charts.
No. Okay, maybe I should use this diagram and explain the idea. So the idea is that we will have here, if you want, at the pass boundary of scribe plus, we will have define what is the supermomenta associated to the out states. Let me call it like this. And then at the future boundary of scribe minus, we will have defined the supermomenta associated to the in states. So
I was sorry. My question was even more naive. I mean, what I was asking is whether you are using two different set of coordinates.
Yes.
And
I will use two different sets of coordinates.
Charts for the whole of space-time, two or more.
So I didn't get the last part.
You're using two different or three different or four different charts to the
charts. Yes.
Yeah, carte.
Mm-hmm.
to describe the whole of space-time. That's the idea.
Yes, I mean the idea is to to be able to focus on this region will be to use these two charts.
Okay.
And yeah, and then at some point relate one and the relate them.
Okay. No, yeah, it was a very simple question.
Okay. So yeah, sorry, I understood charge instead of chart. That's why I started talking about charges. Okay. Okay, so. Okay, so the way we discuss it also, it's actually, I mean, in some sense it was, I mean, one can discuss this in quite simple terms, just in linearized gravity and looking at linearized gravity in harmonic gauge and looking at residual gauge symmetry. So one just looks at vector fields satisfying the wave equation, and of course we are interested in vector fields that are non-trivial at null infinity, And for BMS, we are specifically interested in vector fields that are asymptotically killing. Here, for simplicity, I thought I will just discuss proper BMS. So I will discuss asymptotic killing vector fields, but our discussion was more general and included this generalized or super rotation vector fields that Jeffrey was talking about. But since the interest, I think, was, I mean, mainly to understand super translations, I will focus on proper BMS. So if we impose if we demand that, if we look for vector fields that are both killing, I mean, here the important point, as in the original analysis of BMS, the important point is that one is imposing the killing equation not exactly, but only asymptotically, and this allows for this freedom, extra freedom of super translations in addition to the ordinary translations. So this is the ordinary BMS vector fields, but that here we have obtained them just by looking at these harmonic vector fields in Minkowski space. So these are the super translations, and these vector fields are the ones that describe the Lorentz rotations. So here they are conformal killing vector fields on this round sphere. Now, if we also do the same, we look at harmonic vector fields, but impose the killing equation asymptotically at time infinity now, then we find something a bit different. We find that the general asymptotic solution to both the harmonic condition and the asymptotic killing condition is that we have the vector field should be of this form. So we have a component that is in the direction of partial tau. This is remember at time infinity, this y is the indicates point on this unit hyperboloid. So if here we have some function, and then we have a vector field on this hyperboloid. So the vector field is the killing asymptotic killing condition implies that the vector field is killing on the hyperboloid, and in this way here we recover the Lorentz group, and here the harmonic gauge condition imposes this condition on this function fh, and somehow this I mean, we can understand, I mean, eventually we will relate this fh with this f theta, and here we see that if there was no condition on this function, we will have too many super translations, because there will be some arbitrary function on the hyperboloid, but we know that we only have as many as functions on the sphere of super translation. So in order to cut to get the right number of super translation functions, if you want, that comes from the harmonic gauge condition that imposes this Laplace type equation on the unit hyperboloid. So this curly D is the derivative on the unit hyperboloid. And now it comes what we were discussing before. Now it comes the issue of connecting these two descriptions. I mean, we have a single vector field in space-time that we are just describing in terms of two different set of coordinates, but the vector field there is only one vector field or a family of vector fields. And then when we impose when we impose that the vector field in one description and the other is the same, then we obtain relations between basically the asymptotic value of this function. So we have this function fh on the hyperboloid, and then we get some condition of how the asymptotic value of this function as rho goes to infinity. So as we go to the boundary of this unit hyperboloid, that is related to the value of of the function that we had at null infinity. And similarly for the vector fields. So the idea then is that if we know that this function on the hyperboloid satisfies this Laplace type equation on the hyperboloid, and we know its boundary condition, then we can write it uniquely in terms of this boundary value by some Green's function. So then this is like a again like elliptic problem with boundary conditions, and we get an expression for this function fh as some integral kernel, some g that is given here times the boundary value f theta. Here, this notation y mu denotes the unit vector associated to the point y on the hyperboloid. So if we have, again, the drawing I was doing at the beginning, if we have here the unit hyperboloid, then sorry, this is not this. And I look at some point y on the hyperboloid, then to each point y on the hyperboloid, I can associate a unit vector. This is this capital Y mu. And then Q mu is the null vector associated to the angle, the null vector going in the direction of determined by theta. So this is the type of expressions that appear. And okay. I mean, as I will show later, eventually, I mean, the technical reason why at the end this will work out well with the soft theorem is that this function, this Green's function, is actually related to this Weinberg soft factor, and this is actually how we got it. I mean, here maybe I'm presenting things. I'm trying to be pedagogical and the way we presented it, but of course, the way we arrived at this Green's function was because we knew the Weinberg soft theorem, I mean, the Weinberg soft factor, and I will describe later how this is related to the Weinberg soft factor. Okay, so far this is then, this I just explained to you how then we can extend the BMS vector fields from null infinity to time infinity. Now the next thing is to describe the charges associated to these symmetries or the supermomenta. So this is what I said before. The idea was to generalize the asymptotic phase space at null infinity to an asymptotic phase space at time infinity. And we did here for a free scalar field, but these ideas one can see they extend to other type of massive fields. So asymptotically, the Klein-Gordon equation of a free field with mass m, one can see it implies that asymptotically in these hyperbolic coordinates, as we take this time infinity limit, then we have some power decay in tau, and then we have some oscillatory terms. These are this b of y are complex functions that are actually just proportional to the mode functions if we were starting from a Fourier space decomposition. So these are just the B and B star will, in quantum theory, will be just B and B dagger, the Fock operators of the field. But here we are thinking of them not as Fourier components, but really as functions that live on this unit hyperboloid at time infinity. And now and then the next thing is to have an asymptotic phase space, and then just by the canonical methods, one can find what is the symplectic structure on this time infinity in terms of the free data of the field, which is the free data of the field is given by this complex function. And once we have then the free data for the asymptotic space and the symplectic structure, we can see what, and in addition, we have the action of supertranslation action, that when a supertranslation acts on this scalar, if we just keep the dominant term is when the partial tau hits this exponent here, so it just brings down a factor of im times the function that was multiplying the partial tau derivative. And so this is the action of supertranslations on these both functions, on this free data of the field, and then it is very immediate that this is a symplectic action with respect to this symplectic form, and then one can obtain a corresponding canonical charge or supermomentum. So this will be the time contribution to the total supermomentum. Maybe I stop in case there are any questions. Okay, let me continue then. Oh, and I should say that actually this expression for supermomentum was had been obtained in 98 by entirely different perspective. It was more from a representation theory perspective, and they were working always decomposing the supertranslation function in spherical harmonics and discussing how the BMS algebra one could extend it to a free massive field, and they arrive at, by this different perspective, they arrive at the same action and same charges. Now, just one line of why this, or how this extra contribution from massive fields allows you to extend the original derivation of Weinberg's soft graviton theorem in terms of BMS word identities. So basically, I mean, in showing this equivalence that I'm sure it's been discussed here, there are some key identities one uses at technical level to show the equivalence, and these identities take a different form if the external momenta is massless or massive. So for external massless P, so here Z is the angular position of the soft graviton, and theta is the angular position of the hard momenta. So a certain second derivative with respect to the soft direction gives a delta function in the case of massless particles, and in the case of massive particles, these derivatives give the green function I was describing before. So this is kind of the technical step where one uses to show this equivalence. Okay, so I will, yeah, maybe, yeah, I wanted to sketch, I wanted to sketch how to connect what I just described to this picture I was telling here, and this is also, I think, related to the question that Gaston did. So, yeah, so sorry. So this is This is very sketchy, and in the sense that I only try to work out some of these computations for this talk, but so here I am using the fact that this was supposed to be an informal discussion, so the questions that come will not have the proper factors correct, most likely. This is, the analogous analysis for the case of electrodynamics and charges associated to the large gauge U1 transformations. It's in many places. We did it here, and it's also contained in this paper in the case of electrodynamics. So the idea is that if we look at the supermomentum associated to the out states, so maybe I could add a plus here, but I was always in my talk, I was always focusing on future, on out states for the formulas. So the total supermomentum can be written as integral over the sphere at equals minus infinity of the bonding mass aspect, and if the bonding mass aspect at equals minus infinity can be written as total integral in u of minus partial u of bonding mass aspect plus the bonding mass aspect at u equals plus infinity. So the matching, the conservation law or matching condition that underlies this word identity uses precisely the fact that the bonding mass, that the total supermomentum is defined in terms of the bonding mass at u equals minus infinity for out states and bonding mass for v equals plus infinity for in states. So that is what allows the matching at spatial infinity. But in order to write this supermomentum in terms of the data of out states, then we just do this integration by parts. So this, using Einstein equations at null infinity, this gives the contribution of supermomenta due to the massless fields. And so this then will give the contribution due to massive fields. But I mean, this is just, to kind of close everything, we need to show that this expression here coincides with the expression I just given before for the contribution of to supermomenta due to massive fields. So so this is where I'm going to be sketchy and at least for electrodynamics, more precise, or a version with all factors correct is here. So the idea now is look at time infinity, but now we need to look at the metric perturbation at time infinity, and look at Einstein equations at time infinity. So the stress tensor of the scalar field, if we look at the tau component, one can see that it decays as 1 over tau q, and the leading coefficient is given precisely what the expression we found was like the supermomentum density for the massive field. And then linearized Einstein equations. Actually, maybe these were okay. Okay, sorry. This I don't know if it's a plus or a minus. I'm sorry. Linearized Einstein equations imply some Laplace type equation for this metric perturbation and this component of the stress tensor, which one can then solve via some Green's function that this is now This is now a Poisson type equation on the hyperbola. So given some density, this is like this is a Laplace equation. So I'm mixing Laplace and Poisson, I think. This is Laplace equation for some energy density. So this is the Newtonian version of that equation at time infinity. So we can write then the metric, this potential in terms of this energy density via some Green's function.
And you need d square, not d cube, evidently.
Oh, yes, sorry, I'm very sorry. Yeah, this is important. The three here move here. Sorry. Right. So on one hand, we have then an expression of this potential in terms of this leading component of the stress tensor at time infinity. On the other hand, we need to match. We need to use the fact that we have a single metric in two different coordinate descriptions, one at time infinity, the other at null infinity. And when we demand consistency between these two charts, then one arrives at a condition for what is the asymptotic value of this potential when rho goes to infinity, and this turns out to be related to the bonding mass aspect at u equals plus infinity. And finally, the final piece to close everything is the proper one needs to use properties of these Green's functions. So this what is sometimes called Weik Green's function. If we take one of its points to the boundary of the hyperboloid, it goes into a Weik boundary Green's function with some power. And so altogether, this allows, this gives an expression for the bonding mass aspect at u equals plus infinity in terms of some this integral kernel of the leading component of the stress tensor at time infinity. I think maybe I should say that this is maybe this is just only a fancy way of, I mean, similar formula, I think just appeared in the talk by Jeffrey, where he gave an expression of the bonding mass aspect at u equals plus infinity due to some external scattering particles in terms of the final velocities and masses. So that expression should be an instance of this type of formula, where of course here we are treating fields, so we should have, in the case of point particles, this stress tensor is localized at the position at the velocities of these point particles. But if you see the type of, I mean, we have this inverse, yeah, the type of expressions are the same. Okay, so once we have this, now we can see how the two perspectives on the time infinity contribution to supertranslation match. So we say that if we were coming from spatial infinity and writing in terms of the final data, we were getting we were led to an expression for the supertranslation. We were led to this expression for the contribution, time infinity contribution to supertranslation charge. Now we use this expression I just told you to write the bonding mass aspect at u equals plus infinity in terms of the asymptotic data of the field. And now, and the next thing is simply to interchange the order of integrals. And if we integrate in theta this function, we are led to this what we call FH, the super translation function at time infinity, and this is the expression we have we have obtained from these canonical methods. Okay. So this was this was the part that was a bit sketchy that I tried to work out to present today. Okay. Okay, so maybe a few words about going beyond BMS. So as I mentioned, our analysis was actually, we treated from the beginning vector fields that were actually not just BMS, but we allow for these sphere vector fields, and then we also had expressions for these vector fields, the induced vector fields at time infinity, and how they led to the under charges, and how the corresponding word identities were correctly gave the sublines of theorem. Then the next question, or the one difficulty that appears when dealing with this generalized BMS, is the issue of the algebra, which is also related to Jeffrey's talk. So I mean, even just to get the algebra at the level of the vector fields is subtle, because you need to take into account, basically you need to take properly into account that you are working with some gauge fixing. So once you take that into account, you can get correctly the algebra of vector fields, but understanding the algebra at the level of the charges at time infinity for generalized BMS, that's something that still needs to be understood. Then also the question of loop corrections to charges. So we explore this with Alok in the case of electrodynamics for what will be the subleading charges, and again the case for gravity is also, it remains unexplored. And yeah, so this is about what I had for slides, and now I can discuss whatever people want to discuss. So thank you.
Okay, let's thank Miguel. And are there any questions?
I have one, but it's very general one. So I think it's super cool, this thing of trying to find this super translation symmetry or whatever version of BMS at I+, because obviously it's important to understand scattering for massive particles. Okay, and probably you can get some intuition from what Mark and Cedric have found about I0. I don't know, it's a different point, but probably share some properties. But my question is about, suppose you are interested in understanding a process that involves massive particles and gravitons, or massive particles and photons, massive particles and massless particles. So some of them will go to Sky+, some of them will get out from I+. So, but it should be some, taking into account these mixed processes, mixed in the sense of mixing massless and massive particles, should give some natural boundary conditions, some prescriptions, some intuition at least to give some matching condition there. Is there some at least intuitive way of?
Maybe I can go back to this formula here. So you can think that you always start with the supermomenta defined at spatial infinity,
yes.
And then when you integrate by parts, this will give you this part here that is integral in U of partial U bounding mass. When you use Einstein equations at null infinity, this precisely gives you all the energy flux due to all your massless fields. So all the massless field contributions appear here.
Mm-hmm. Okay.
And then, yeah, and then the second term is due to massive contributions. Yeah.
But okay, can you understand better what is the use of using, you know, time like infinity on top of null infinity? In other words, you have information on the Bondi mass aspect from Sky Plus, right?
Yes.
You have all the information. So yours, it looks to me, is just a rewriting in a different set of coordinates, quantities that you have access to also from Sky Plus. So I wanted just to understand the use or the advantage of having this formulation.
Right. I mean, yeah.
It's a very
yeah,
naive
of course.
question.
No, it's not. I mean,
hear about it.
no, it's not. Yeah. I mean, the thing is, yeah. So, okay. So of course, the use of these things, I think, or one of the main attractiveness of these things is that we have this conservation statement between total incoming supermomenta and outgoing supermomenta. Now, usually when we these incoming and outgoing charges, we express them in terms of our the scattering data, incoming scattering data, and outgoing scattering data. Now, this scattering data doesn't involve the Bondi mass aspect. I mean, for gravity waves, of course, if you know the Bondi mass aspect, I agree with you. But if you are thinking in terms of relating incoming and outgoing scattering data, for gravity, what we know is the gravitational waves or the shear, right? So what Jeffrey was calling CAV. So yes. when we have these Einstein equations, will tell us, okay, here again we'll probably get the signs wrong, but depending on what were the conventions, here we will get something that is the square of the News tensor at null infinity. Mm-hmm. And so this is the contribution. So eventually, at the end, we will write our full supermomenta in terms of some integral of this new square plus some integral, so this is at Sky, plus some integral of this stress tensor of massive fields at time infinity. So, I mean, if you want to write your charts in terms of only your outgoing data, then this is useful. I don't know if that.
Yeah, but I mean, in the first equation, M is the aspect, right?
Bondi mass aspect, yeah. So
then there is an extra term, right?
Oh, it's sorry, yes. Yes, totally, yes. There is the soft term, right?
Well, which integrates, whose angular integral is 0, but
yes.
I understand it contributes to the.
Yes. Sorry. Yeah, this is. Yeah. Sorry, I
so
was
you can,
only.
I think in that formulation you can also recover what is PF plus.
Right. So this is plus or minus dv squared n. Right. So I'm saying that if you are given, all I'm saying is that if you only know the news or the outgoing gravitational radiation, then you don't know. I mean, if you don't know. You don't know the value of the mass aspect at U plus infinity. I mean, but it is given in terms of your outgoing
massive
field, right?
I see.
Maybe I'm in a better position to say Miguel's work is interesting than he is, because I don't have to be modest. but I, you know, I certainly I found it incredibly interesting, and one of the, and sort of surprising that there's been all this discussion in relativity about resolution of spatial infinity, but not so much of time-like infinity. And what was really nice about this is, you know, this hyperbola, of course, I mean, he didn't really use this language, but, you know, it's Euclidean anti-de Sitter space. And the thing he convoluted with was, you know, the bulk to boundary propagator from the bulk, which is the hyperbola, to the boundary, which is the sphere at null infinity. So it's not only been mathematically useful for a lot of things, it also brings it much closer to, you know, a lot of ideas that have been being explored in holography. And yeah.
And then it also extends your way of deriving the soft theorems in a very natural way, if I understand, in a very
yeah. So we had a formula which in the paper he, you know, that involved some weird sort of non-local thing in the celestial sphere, which we didn't recognize as the bulk to boundary propagator for anti-de Sitter space. And that was explained why we had this weird, I mean, we just kind of worked it all out with brute force, and we had this result. It's like, oh yeah, that's the bulk to boundary propagator on the hyperbola, which came afterwards. I might also add in the question about, you know, massive particles have to go to time-like infinity if they're in energy eigenstates, but we can also discuss massive particles in, you know, conformal primary wave functions that are in boost eigenstates. And indeed, there are, you know, solutions of the massive wave equation for which the Klein-Gordon flux goes not to time-like infinity, but to null infinity. And that doesn't contradict anything because they don't have finite ADM energy, they have finite boost energy. And so they can and must go to null infinity. So there is a way of formulating everything where, you know, everything lives at null infinity and you don't really need to talk about time-like infinity. But I think there also should be a way of formulating everything where, and I guess maybe this is a question. You drew that picture with the hyperbola at the top, you know, you cut off the top and then you did what, which we now understood better, the H0. So this is sort of a hybrid of the bulk picture and the boundary picture, but you might want to press that cap down and press H0 up. And then you have some other way of looking at things in which, you know, that's the hyperbolic slicing that De Boer and Solodukin talked about, which I guess was maybe one of the first. So then there's another picture where everything is described in terms of, I don't know how we fit all these pictures together, but right. So there might be one complete story which involves H plus, H minus, and H0, which describes everything we want to know about the. I mean, the way Miguel has drawn it, the cups go down, but as you vary the parameter of the resolution, the cup goes up and starts to hug null infinity. So you can write the boundary of Minkowski space. You can think of it as the sum of these three pieces, H0, H plus, and H minus, and that's a whole other way of thinking about general relativity. Which maybe this is a step, hopefully a step toward.
By the way, I would like also to ask, so is there for any super translation f of theta a conservation law between I minus, chi minus, and h minus, something, an integral, the sum of h minus, equal to something of h plus and chi plus?
Yes.
Trivially, but you had like linearized, particle, you mean for a nonlinear interacting massive particles, and is there really a conservation law for any function on the two string?
Yeah. So although I presented it for linearized gravity, I think that if the fact that this soft theorem or its classical versions that I think have also been discussed here, that expresses this zero.
No, but this is like linearized gravity. So I want to.
Sorry. I thought that. Sorry. Yes. Okay. So maybe let me.
Is there really a BMS symmetry with massive particles and massless? Okay.
Yeah.
That's with a conservation law, not a balance law.
Yeah, I think so. I mean, sorry. This factorization property or the classical version, it's I understand is valid in full. In nonlinear GR, right? I mean, so as long as this property is true, then this conservation is true.
When you write that commutator equals 0, it means the S matrix commutes with those charges?
Yes. So yes. So this was in the language of
Thibault is asking.
Yes.
Yes. Right.
Yes.
That
I mean,
sum.
Yes.
I mean, yes. Well, that sum is the same at time equal minus infinity as it is at time equal plus infinity. Is that so?
Right. So the full, we are saying that the full PF, which is the sum of these two contributions, I mean, classically, we will say that the full PF evaluated at minus infinity equals the full PF evaluated at plus infinity. And this should be valid in nonlinear GR.
Also in nonlinear GR. Well, that's a
yeah. This statement is true in full nonlinear GR, the classical statement.
Okay.
Isn't it true in nonlinear GR just because the fields are weak?
Yes.
Everything disperses and become weak near all the boundaries.
But and it does not prevent any scattering. I mean, you are sending massive particles, let's say initially without massless, then you have radiation and massive particles, and you have infinitely many conservation laws, I mean, uncountable conservation laws for in-out thing.
Yes.
That's a lot.
Yes, but I think
that's a lot, and that's what. But remember, the vacuum carries these charges. So
and some of these P's are like vacuum. I mean, they are like non-informative. I want something which involves quantities like momenta, incoming and outgoing momenta. There are non-local things. You are saying there are non-local things that.
Oh no! I didn't say non-local.
Hey.
Well, I mean, wait. What do you
memory
mean?
Is
charges are measured in infinity.
Yeah, I guess if you call memory non-local, then it's true. But so this is this formula for the memory for this formula that tells this shift in the metric perturbation in terms of this factor. This is, I mean, we are reinterpreting this statement in this conservation language. Of course, in your incoming and outgoing data, we need to include not only the momentum of particles, but also the gravitational fields. So what the reason why it can be conserved is because the final, this final piece of the metric field adjusts itself so that this holds. I don't know if that.
So is it a conservation law, or?
Right, yeah, because.
In what sense it is a conservation law?
Yeah, so
yeah, because
there's a number you can construct from the incoming data, including massive particles, that equals a number that you construct from the outgoing data, including massive particles. And
yeah,
and you can measure that conservation law. That's the memory effect.
Yeah, I mean, the question is, if you have an infinite number of conservation laws, sometimes you say the problem is integrable, and but I mean, you are not telling me that the S matrix for two particles colliding and emitting all sort of gravitational waves is integrable.
No, because the statement is equivalent to Weinberg's theorem, and Weinberg's theorem doesn't tell us that the S matrix is integrable.
Yeah, and also the Weinberg solved theorems, as Ashok Sen has pointed out, you can easily do it if you know the initial and final state. But
yes.
Here you don't. I mean, you have to solve the bulk problem to find the final state. And then on top of that, also what is the soft radiation. But at least that's how I see it.
Right. But that is why it's precisely why it's a conservation law, right? In the sense that you know that these two quantities will be equal even before doing this evolution, even without solving this evolution problem.
Right. So but then it becomes, less useful as a statement because it doesn't.
Yeah. But that is true for all soft theorems in some sense, where the idea.
I don't think it's any less useful than any other conservation law. It makes a prediction that there's a memory effect. It's completely equivalent to that statement.
Okay.
Yes.
No, that
yes.
As long as the memory effect goes, I agree fully. Yeah.
But the soft theorem Weinberg's, as it is written here, it's not first order in G. There is an expansion in G.
It's amazingly exact.
It's exact statement, yes.
Yeah, it doesn't have any corrections.
Yeah, Thibault. I mean, somehow there are higher orders in G involved in the fact that the initial momenta change, in the final momenta.
Yes.
One by order G. So actually the effect is of higher order in G.
Actually, yeah, in that sense, this is a non-perturbative statement in the sense that you're summed over the equation of, I mean, your final momenta, if you write in terms of initial momenta, you have all orders in G incorporated.
Right. No, I think I agree. This seems to be exact. Yeah.
Miguel, can I ask a short question?
Yes.
So this Green's function expression that you wrote for the mass aspect in terms of the stress tensor of the matter, so is that for linearized theory or is it like exact?
I mean, this derivation I was giving was for linearized. I
think, sorry, I think it works because the fields die down with as some order in 1 by tau. So even if you add nonlinear interactions, then these expressions will not change.
Exactly.
Right, because the particles are too far from each other.
Yes, effectively.
Okay, thank you. But is there a proof of that? I mean, is it obvious or?
I mean, okay. I mean, it's because the field goes as 1 by tau to the 3/2. So if you add interactions, you can check that the nonlinear interactions will die down fast at time like infinity. And that would not.
Right. By this, you will see that. Yeah, somehow we like wrote it down in paper in the case of my electrodynamics, but a similar argument goes here that for the leading of theorem, these higher, these nonlinear contributions do not contribute, but then you will have contributions for the subleading terms.
Not subleading, but sub-subleading. Maybe not subleading, but sub-subleading.
Okay.
All right, are there any additional questions? Okay, maybe let's thank Miguel again